back some old notes. This was from the one-sided limits that we did earlier. And I wanted to talk about continuity. Okay, so when is the graph continuous? When is it connected? And when is it not continuous? When is it disconnected? So I'm going to look at this graph and let's talk about it. So from here, that arrow means it keeps going forever without breaking. So it's continuous from negative infinity. Is it continuous at 2? No, definitely not. And then it becomes continuous again. Is it continuous at 4? No, it's not connected. And I really want to talk about that because the limit existed there, but the limit and the point weren't the same. And then it's continuous. Is it continuous at 5? Yes, it is connected. So notice at 5, the limit from the left, the limit from the right, and the point at x equals 5 is the same. Notice at x equals 0, the limit from the left was 2, the limit from the right was 2, the limit overall was 2, and f of 0 is 2. So at 0 we are continuous. So right now we just want to kind of write down that definition. F is continuous at some number A if, what are the conditions? Well, the first thing I'm going to put down is that f of A is defined. In other words, there is a point. If there's just a hole, then definitely it's not continuous. Step 2, the limit as x approaches A must exist. The left side and the right side have to meet at the same place. We don't want any of this business. Then the last thing I want to state is that the limit has to equal the point. Now, if it's discontinuous, there are several ways that it can be discontinuous. So I want to talk about discontinuity. Okay, so I'm going to draw a couple of graphs here. Let's say I have this one. This is not continuous, and that is because it has a well, I'll do the reasons why. Let me draw my pictures first. That will save some time. Just drawing 4 quick graphs. Let's do one almost like that one. So here's another example of discontinuity. I have a line, it has a hole, but there is a point that exists, it's just not where it's supposed to be. Another type of discontinuity could be what we saw just a minute ago, where we have the graph going up. Maybe it even exists here, but doesn't exist there. So the limit does not exist on this one. And then We could also have maybe something like this. So let's think about these types of discontinuity. These two are very, very similar because it has a hole. These are called removable discontinuity. Oh, I can't spell continuity. And that just means we have a hole in the graph, but everything else is connected. This one is called jump discontinuity. And the last one that has an asymptote there is called infinite discontinuity. Now, I'll do some examples of looking for continuity, but I do want to specify that sometimes you'll be asked, is something continuous on a certain interval? So we're just looking in that range. We want to make sure that everything in there, it is continuous. Or it could say it's continuous on its domain. So in that matter, if we had a rational function and they had already stated that x is not 2, then it's continuous everywhere that it is defined. So it's continuous on its domain, but it's not continuous at that point. It's continuous everywhere else. So there's a little bit of stipulations on the wordings. So you want to be careful whether it's asking you, is it continuous everywhere? Is it continuous on its domain? Or if it's specifically asking for a single point or an interval.